Hey guys, so here is our video. I'm starting on slide 37 of the intro to solubility PowerPoint, so 37 through 44. So the last part, or the last time we went over intro to solubility, we talked about, generally talked about how temperature and pressure can affect solubility. Now we're going to go into the details. So let's do temperature first. So as you can see, when we have a liquid solvent and a gas trapped inside it, or a gas dissolved in it, so a gas solute in a liquid solvent, if we increase the temperature of the liquid, we decrease the solubility of the gas. Okay, so you think about this, because if you increase the temperature, okay, and the gases are just kind of floating around inside, let's say the solvent is water, then the gases are going to be moving around much more quickly and faster, because increased kinetic energy. And if that occurs, then gas particles will be further away from each other. As you can see, from 50 degrees, we have gas particles that are like so, but at 70 degrees, as you can see, and this is water, by the way, so liquid outside. As you can see, the gases move apart faster, and some of it actually escapes the water, so there's more space inside, so the solubility decreases. Okay, and for solid solute in a liquid solvent, if we increase the temperature of the liquid, we increase the solubility of the solid. This is because if we increase the kinetic energy, okay, first of all, we know that solubility has to do with the random motion of solvent particles pulling apart solute particles. That term is called solvation. So if you increase the movement of the liquid particles, it's going to move very fast, which increases the chances of, or which increases the frequency of random connections between solvent and solute particles. Hence, that's going to cause better solvation, hence increased solubility. Okay. This part over here, we already went over, just looking at the three types of saturation levels: unsaturated, saturated, and supersaturated. And we already went over this, but in order to make a supersaturated solution, all you need to do is keep adding solutes until no more can dissolve. Okay. Pressure, that's the second factor or variable. If you increase, again, we're talking about gases. If you increase the pressure of a gas, okay, if you increase the pressure of a gas that's above a liquid solvent, you're increasing the solubility of the gas. Okay, remember, if you think about squeezing, if you squeeze, okay, or if you raise the pressure like so, you have less space. Less space means more random motion, so it's going to, or faster, or more frequency. Okay, and since all particles are randomly hitting everything, if you have more frequency, a better chance or higher chance of solvation. Okay, so the gas particles are going to move around much more quickly, or not much more quickly, but it's going to move around and hit the liquid much more frequently. Hence, the solubility increases. Next is polarity. So for polarity, we didn't go over what exactly that means, what exactly it means. So there's only one thing I want you to know. First of all, I'm just going to tell you what polarity is, but we're going to go over it second semester. So I'm going to just give you like a very, very basic definition, okay, in layman's terms. So polarity is when one molecule has polar or has two sort of poles, so like a plus side and a negative side, and this is a positive and negative side. So this has to do with electrons. Okay, some electrons are hanging out more so on the right side, hence this side will be more negative than the left. Okay, so all you need to remember for polarity for now is that like dissolves like. Okay, so polar solvents can dissolve in polar and ionic solutes, because ionic and polar are the same thing. So polar with polar, and nonpolar with nonpolar. That's all you need to know. The fact that like dissolves like. Polar solvents dissolve in polar, nonpolar dissolves in nonpolar. Okay, all this other stuff, we'll go back to it once we learn polarity. And this is how soap works. Okay, water is polar, and all your grease and everything, your soap scum, or not soap scum, your oils is nonpolar. And soap is sort of cool looking because it's kind of like a lipid bilayer without the actual bilayer. It's like a single layer. And if you remember from hydrophilic liquid bilayer, phospholipid bilayers have the hydrophilic head and the hydrophobic tail. So soap has one side that is polar and one side that's nonpolar. So the nonpolar side will attract all the grease and oil, while the polar side attracts the water. So because of that, the soap can kind of trap all the oil inside the nonpolar side, and then the outside will dissolve in water. Hence, all the oils and dirt get washed out. Lastly, factors affecting dissolution rate. So dissolution, it means dissolving, right? So dissolving rate. So these are all fairly common sense, but I want to point them out. So if you think about how you can more quickly dissolve something, the first thing you can do is to increase the temperature. Okay, obviously if you heat something, more kinetic energy, so it's going to dissolve. Solvation is going to be will have a higher frequency, so it'll dissolve faster. If you stir, obviously that's also increasing the temperature, increasing kinetic energy, so greater dissolving, and increasing the surface area. So what this means is, if you have a large cube and you break it apart into smaller cubes, there's more surface area total if you add up, because there's so much surface area that's missing from the inside of the cube. But if we were to break it apart into smaller cubes, we have a lot more surface area. Hence, since there's more solvation happening where the solvent particles are hitting the solute particles, there will be a greater dissolution rate or greater dissolving. Okay, that's it. Peace out, y'all.